All right, so let's go over these concepts: arc length, sector area, linear velocity, and angular speed. And then once I've talked about them a little bit, I'm going to do all these problems that are in the homework, taken them out of the book, pasted them here onto my little screen, and we're going to do them together. The arc length of a sector of a circle, of a little piece of a circle. Let's draw a little circle here. All right, so the arc length is, if you look at just a little piece of it, the arc length will depend on the radius and the angle that is subtended by the arc. So if you have your angle theta here, and then S is the arc length here. I always use S for like a distance in math and science. A lot of times I do. So this is S, and then we're going to say R is the radius, and theta is the angle. Theta is in radians. Has to be. Otherwise none of this works. Then the formula is S equals R times theta. Now the area inside is 1/2 R squared times theta. The linear velocity, so the velocity of an object going in that certain amount of s in a time t, the linear velocity v is s divided by t. So the distance divided by the time. It's just like velocity like on a car. And then how fast the angle is changing is going to be the angular speed. That's theta divided by time. Theta, also radians. All these are in radians, okay? Now, since S is R theta, we have S being R theta, and V is S over T. I'm going to put those two together. I'm going to replace that S in the V equals S over T with R theta. If you have a fraction like that, R times theta over T, I can make it R times theta over T. And now theta over T is just W. So this is R times W. So what this says then is V is RW. So we get another formula out of this. So let me box all the ones that you need. You need this one. You need the area of a sector. And you need velocity is, you need the linear velocity, you need the angular speed, and you need this one, velocity, the linear velocity in terms of the angular speed. All right, so let's see how this is used in practice. Let's do the movement of a minute hand around a clock. So essentially we have a clock here. All right, good enough. Just leave that. Let's just suppose that's a clock. I can make that look a little better. There we go. Okay, now it has a radius. So the minute hand is like this, and it's moving around in 25 minutes. So about 25 minutes. I'm going to just do the 25-minute one. So read the problem. You might want to pause the video and read the problem. So it moves around in 25 minutes, and so 30 minutes would be half of it, so 25 may be about right there. So it says, how far does it move in 25 minutes? Well, that's the arc length here. The arc length. And so what we need is S equals R theta. Well, they tell us that the minute hand is 6 inches here, but we need theta. We need what is this theta value? What is this theta in 25 minutes? Well, we know that 25 minutes is over 1 times, let's see, in 1 revolution. Well, let's see. 1 revolution is 2 pi radians. So I need to get radians out of this, okay? Well, I need to get rid of this minutes here. You get rid of the minutes. So there's 60 minutes in 1 revolution. All right, and so you figure this out, and you'll get theta out of this. So this will be what your theta is. You multiply times r, and you're done. So that should start you out. Well, I'll just finish it here. This is going to be 20. So let's see what cancels here. So the minutes cancel, the revolutions cancel, and you're just left with radians. So what you get out of this is 25 times 2 pi over 60, and all this is just radians. So we take that, plug it into this formula here. So then S is R is 6 inches, times 20, let's say that's 50 pi over 60, pi 60. Okay, and let's see, that's inches. And then whenever you write this, the radians isn't always written, okay? So yes, there's radians right there, but we're just looking at how far does the tip move? How far does it move? So the radians isn't written, we just write inches. And so when you do the math here, you get 15.71 inches. That's the answer. Okay, let's look at another one. Okay, so I will start you out on this one. Let's make a circle again. All right, so it says the arm and the blade of a windshield wiper have a total of 34. The blade is 25 inches long. Okay, how much window area can the blade clean? So what's happening here is you have a blade. You have the windshield wiper has a total length, the arm. So the arm is going to be in green here, and then I'll do the blade in red. So the blade is 25. So it's 25 is in red there, and then 35 here is in green. This is 34. All right, and so the blade is making a circle around, it's making this area here. That's what the blade's doing. And then this inside here is 9. So this is 9 here, because 34 minus 25 is 9. So what I need to do is I need to delete out this inner circle here. So what I'll do is I'll find it's not going all the way around now, right? It's going about 120 degrees. So 120 degrees is less than 180. So let's say it's going out this much. So let's say that much is 120 degrees. So that length is 25. And let's say that this is 120 degrees. All right. So we need to find out how much area is in basically that outer shell. So you have circle, you have an inner shell. We're looking at what's going on, how much this is basically. Okay. Well, the whole thing would be 34, right? So you have area is 1/2 r squared theta. So that would be 1/2 34 squared. Now theta has to be in radians, and 120 over 1 times pi over 180 gives us 2 pi over 3 radians. So I'm going to put 2 pi over 3 here. All right, so we get an answer. And then the inner part, the interior, would be using that 9 instead. And then you can figure it out from there. Okay, so ... All right, so let's try another one. So for this one, once again, we have a circle. So let's draw a circle. All right, and an object is moving in a circle with a radius of 5 centimeters. So we've got 5 here. If in 20 seconds a central angle of 1/3 is radians swept out, so 1/3 of a radian. So we'll call this theta. So theta equals 1/3 radians. What is the angular speed of the object? Well, W is theta over time, and it says 20 seconds, so it's 1/3 radians over 20 seconds. So you finish that out. And then what is the linear speed? V is S over T, but it's also equal to R times W. So it seems like you would take whatever you got for W and multiply times R, and then you got it. All right, let's try another one. So here we have the moon going around the Earth. So the way I would draw this is I would draw the orbit of the moon around the Earth, where the Earth is here, and then the Earth is the center, and the moon is on the outer edge. Okay, so let me draw the moon in red. All right. Now the distance between the moon and the Earth is so large. This is 2.39 times 10 to the 5th, which is like 239,000. It's so large that you can disregard the radius of the Earth in this, because that's only, it's about 5,000 miles, I think. So we're going to assume that the Earth is just a point. Okay, so the moon is moving around the Earth, and it says, so this radius here then is going to be that 2.39 times 10 to the 5th. That's the radius of the orbit, basically. And it says 1 revolution takes 27.3 days. So it says find the linear speed of the moon. Express your answer in miles per hour. So the linear speed is going to be v. Linear speed, linear velocity. So that's r times theta. Well, its velocity is s divided by t, but it's also r times w, sorry. Okay, so it would be helpful if we got w. Well, anytime they give us how many revolutions in a certain amount of time, you can get w out of that, because that's how many times you're moving around something. That's how fast you're moving around something in an angle sense. So when they talk about revolutions, w is involved, okay? So 1 revolution in 27.3 days is, you multiply that times 1 revolution is 2 pi radians. And see, now you have radians per day. And now they want it in miles per hour. The miles will come from the radius. And then the per hour, you just convert days to hours. So 1 day is 24 hours. And so what you can get out of this then, so the W, write that better, W is revolutions per day. You convert that to radians per hour. So let's see if things canceled here. So revolutions cancel, and then days cancel, and you got radians per hour, and that's what you need. So you multiply all this out, so it'd be 2 pi over 27.3 times 24, and the units would be radians per hour. And then once you plug that into this W here and multiply times R, you'll get some number here, and you'll get miles, because that's come from the radius, per hour, and that's what you need. So that should set you up for that problem. All right, so let's try the pulley problem. So you might want to read it first. Maybe you already have in the book. So let's draw 2 pulleys. Okay, so what it says is that the small one has a radius of 2 inches, and the large one has a radius of 8 inches. Now, we're trying to find the fact that if the smaller one is rotating at 3 revolutions per minute. So I'm going to say, I'm going to use V, R, W, and theta for the small one. And I'll use V bar, R bar, W bar, and theta bar for the large one. Okay, so we'll use that. All right, so let's see. If the 2-inch pulley is caused to rotate at 3 revolutions per minute. So it's 3 revolutions per minute. So far we have that W is equal to 3 revolutions per minute. I'm going to go ahead and convert that to radians. 2 pi radians is 1 revolution. So basically that would be 6 pi radians per minute. Okay. Now it says determine the revolutions per minute of the 8-inch pulley. All right. So if W is 6 pi radians per minute and the radius is 2, then we know that V is RW. So this means that V must be 2 times 2 inches times 6 pi radians per minute. And so V is 2 inches per minute, 12 pi inches per minute. Inches per minute. Remember, for velocity, you don't include the radians. All right, now we have that for the small one. Now, the large one, the linear velocity is the same. So the rope, or the cable, sorry, moves around the large one in the same speed as the small one. It's just that the angular speed is different. And that's what we're trying to find. Determine the revolutions per minute of the 8-inch pulley. The revolutions per minute is the angular speed, basically. All right, you convert it to that. So revolutions per minute. Okay. So now for the big pulley, we have, I'll just do this in a different color, like maybe green. So for the big pulley, we have V bar is equal to R bar times W bar. Okay. The velocity is the same, so it's this one. Right, so that's going to be 12 pi inches per minute is equal to R bar, which is 8, times W bar. So when you do 12 divided by 8, that would be 12 pi inches per minute divided by, this is 8 inches. 8 inches. So that would be, the inches would cancel. You get 12 pi over 8 revolutions per minute. That's radians per minute. Sorry, radians. Because the radians is written. The radians is in here. But you don't write it. This is radians per minute, which is, let's see, if you take out a 4 out of each, you get 3 pi over 2 radians per minute. Okay? Now, there's 1 revolution, so this is so far, this is W. And so we want to convert that to, so far we have W bar, which is the large one, is 3 pi over 2 radians per minute, but we want revolutions. So this is times 1 revolution is 2 pi radians. So the radians would cancel, the pi's cancel, and it looks like you're going to get 3 revolutions over 4 minutes. So 3/4 of a revolution per minute. And I think that's what they wanted. Revolutions per minute. Yeah, 3/4 revolutions per minute. That's how you get that. Alrighty. So now let's look at another one. I think the other one was up here, cable cars in San Francisco. All right, what do we got here? Each cable travels at, driven by a rotating wheel. Let's draw a wheel. And then we have a cable that comes off of it. All right. Now it says that the diameter of the rotating wheel is 8.5 feet. So what that means then is that the radius is 4.25. So R equals 4.25 feet. And it says the cable travels at a speed of 9.55 miles per hour. So the velocity of the cable is 9.55 miles per hour. Right? How fast is a wheel rotating? So that's W. So what we want is W. All right. So, but we want it in revolutions per minute. Let's see. So we have that velocity is R times W. Velocity is 9.55 miles per hour. And this is equal to 4.25 feet per, that's just 4.25 feet times W. All right, so let's divide. So this means then that W is 9.55 miles per hour divided by 4.25 feet. So that's over 1. So this would be 9.55 miles per hour times 1 over 4.25 feet. This is going to be W. So they want W, though, in revolutions per minute. So what we need here, then, is to convert all this. So revolutions per minute. We need revolutions per minute. So if I convert now miles, there's 5,280 miles per feet per foot. Sorry, there's 5,280 feet in 1 mile. So I've gotten rid of the miles and the feet. And now I probably need something else. I need revolutions per minute. So now I got to get rid of the hours. So there is 1 hour in 60 minutes. So now I've gotten rid of the hours. So I've got minutes, and now I need revolutions per minute. So if I take this and I multiply times 1 revolution is 2 pi radians. Let's see what I get here. So let's see. If I do all the math on a calculator, I get 31.47. Now let's see what units we have. We have revolutions per minute. Yeah, revolutions per minute. RPMs, basically. Remember, the radians isn't always written, so you don't need to worry about it. So this is the answer. All right, I hope that helps.